First thing I'll hit are a few of the announcements. First, I've mentioned this many times before. Miss Gerasi is working on getting a strong math team together for next fall's competition. If you're at all interested, they're meeting every Friday at noon on the Birmingham West campus in the C building, that's the science building, C100, and every Monday afternoon at 3, same place, C building, Birmingham West campus, C100. If you want to have any practices out here, we can go through them here too, just during my office hours. But right now, like I was saying, I'm so low in energy, I may be home sometime during office hours, but I'll try to let people know if I'm going to go, because I am dragging a little now. Okay, so anyway, meet with Mr. Rossi or me. Now, Thursday afternoon from 2 to 3:45, we're supposed to have some training here down at the way at that end of the hall. So if you are looking for me on Thursday, I may be in that training from 2 to 3:45. I don't know if I'll have the energy to stay for that, or if the room fills up, I want the younger folks to have opportunity for the training, and I won't take a seat. Now, this has a sort of a double-edged sword to it. I'm going to be talking about tutoring services, okay? In some of my other classes, some of the students really need this. In this class, I would say you folks can be tutors, okay? So let me tell you about both campuses now. First, on this campus, there's 2 places you can get tutoring, which of course also translate to opportunities for you to tutor. One is about 2/3 way down this hall here. In fact, if you go out into the long hallway there, you'll see there's 2 exit signs in the middle of the hall and the one at the very end. The first one goes down toward the student services area. The second one goes toward the cafeteria area. Don't go down that way. On the right, past that second one, right across from the stairwell going down, is room 202, and that's the SSS, that's Student Support Services Tutorial Lab. They will pay you to tutor, okay? And it's a decent amount. And since y'all have had a fair number of math courses behind you, yeah, you can tutor anything you've made an A or a B in math, and English and other things as well. So if you want to pursue that, check with Miss Holland. She's the tutor coordinator. But if you need tutoring, either for trig or something else, you can also get tutoring there. And so that's one. Now, that same stairwell I was talking about, the second one down there, rather than going to the right, and that's the SSS tutoring lab, if you go down that stairwell and go both levels down, don't get off at the cafeteria level, go on down to the very next level, and as soon as you come out of that, take an immediate right, and right behind you there is the Space Center. There's a big sign there. It says Space Center. I think there may be double doors that sometimes are open, sometimes are closed, but that's the Space Center. They provide tutoring, and they also hire tutors, okay? I don't know if they're hiring, but it sure looks like from this they should be, okay? Because this is saying in the Space Center, the Bachelor tutoring schedule is Monday, 12 to 4. And Mr. Tariq Lake is doing that, and it says developmental math. Now, he's been in my calculus class, so he can do higher than developmental. I don't know if they allow him to, but he should be able to. But that's 12 to 4. There's also a lady down there doing English. And then on Tuesdays, from 10:30 to 2:30, they have Mr. Etheridge Means, who was an adjunct instructor for us, and now he's doing tutoring for us. So he's a professional, and he does all math levels from 10:30 to 2:30, and nothing Wednesday, Thursday, or Friday. So it looks like they probably have some openings if you're interested in tutoring. I don't know how the 2 places compare in what they pay. I would guess they'd be about equivalent. Okay? So that's on this campus. Are any of you on the Birmingham campus? You are, okay. Over there, there's 3 places you can get tutoring. The first is in the SSS, sort of like ours here, except I think that's mostly developmental math tutoring. I don't know if they tutor upper level math or not there. But that's in the C building on the Birmingham West campus. That's between the library building and the B building, and it's the door closest to the B building, the academic building. It's C104 or 106 or something right there is the on that side. Okay, the C building is really short. Okay, so that's where SSS tutoring is. Now there's also STEM lab. That's in the B building, just real close to where the SSS tutoring. Go into the B building. When you take a right around the corner, first door on the right, B112. I don't know what hours they have it, but and I know that's upper level as well as developmental math. So you can get any kind of tutoring there, or you can tutor there. Okay, their SSS lab, I think it's mostly Mr. Harris that tutors there. I don't think they hire students, but the others we can. The SSS, STEM lab, I think will hire people. Now, I don't know if you have to be in the STEM program or not. Don't know that. But then the third place over there is in the Leon Kennedy Center, the student center, where the cafeteria is. Up on the second floor is the bookstore, but also the Space Center there. And that's where this is listed. And they have tutoring there all 5 days of the week. Now, if y'all are interested in that, I can let you see this. Some of these say developmental only, developmental math, but Mr. Means is over there Monday from 10:30 to 2, math all levels. Again, Tyreek Lake is there just about every day too. Mr. Means is over here on Tuesday, so he's not over there on Tuesday. Over there on Tuesday would be Tyreek Lake from 1:30 to 5. It says developmental math, but I'm sure he can help with the other as well. Mr. Means is there 10:30 to 2 on Mondays and Wednesdays and Thursdays and 10:30 to 12:30 on Friday. Okay. He also tutors chemistry, I noticed. So all levels of math and chemistry. So they probably doesn't look like they need any additional tutors, but you can check with them and see if they do. But over here it looks like definitely they would have some need for that. All right. I hope y'all realize it is homecoming week. Okay. And already last night we had a basketball game. I know the women won. I didn't ask about the men. But other things coming up today, for instance, in fact, happening in just a few minutes, will be the scholarship and transfer information in the faculty staff dining room here on this campus. They say it starts at 10, but they don't say how long it goes. But if you miss that, you can catch somebody on that as well. Okay. This evening there's a comedy show. Mr. Lawrence Jackson featuring Miss Maddie J. I don't know anything about either one of those, but that's at 4 p.m. this afternoon at 4 p.m. in the A.G. Gaston Auditorium, which is on the Birmingham East Campus. Okay. Tomorrow, in our cafeteria at noon, name that tune, and then on the Birmingham campus, More Than History, the speaker is Mr. Eric Guster, and that'll be at 12 o'clock noon in the ACAT auditorium on the Birmingham West campus. And then Thursday, I'll let you know about that on Thursday. If you need to see this, you certainly, they have them posted all over the place. So, and there's activities on Friday as well. And I believe there's another basketball game on Monday. Yeah, next Monday. Also, Lawson State versus Gadsden State. Okay, good deal. Any questions on anything, including trig? All right. Okay, here I think is where we left off last time. So let's get the graph set up, the PowerPoint set up for the current slide. We're going to talk about the graph of the cotangent function. Okay? Now, let's think about this a moment. The graph of the cotangent function is very similar to the graph of the tangent function, not as similar as sine is to cosine. I mean, they look almost identical. It's just there's a little phase shift there. Okay? Tangent and cotangent, they have some similarities, and here's partly what they are. Number one, they both have a period of pi. They're the only two trig functions whose normal period is pi. All the other fours are normal period is 2 pi. Okay? Here's the difference, though. If you think about what cotangent is the quotient ratio identity or ratio identity cosine divided by sine. Okay? And just like the tangent function was sine over cosine, so everywhere cosine was 0, tangent had vertical asymptotes. Where was cosine 0? At the half pi's. Well, the cotangent function has sine in the denominator. Where is sine 0? I like the sound of this better. What? Okay. At the whole pi's. I like whole pi's better than half pi's. Never mind. That's just a joke. Okay? So, the sine is 0 at the whole pi's. At 0, pi, 2 pi, 3 pi, negative 2 pi, negative 3 pi, all of your n pi's. Okay? So, but that's the same with sine and cosine. There is a phase shift type thing going on. Whereas tangent has vertical asymptotes at the half pi's, cotangent has vertical asymptotes at the whole pi's. But that's not the only difference. That was it for sine and cosine. But for tangent and cotangent, you have something else going on. Let's think about it. Where does cosine usually begin? At 1, okay? And where cosine is 1, though, that's where sine is 0. So you're not going to have that because you can't have it at 0. But cosine is positive there in the first quadrant. And it starts off a 1, and it just can't be 1 because of that. But anything to the right of that, both sine and cosine are positive, so cotangent is positive. But if you think about this, if cosine is just a little bit past 1, then sine is just a little bit past 0, so then you have a number close to 1 being divided by a number very close to 0, meaning a very small number, both positive. That puts your cosine going to positive infinity. Okay? So, just past 0, cotangent is infinitely large. But then it decreases because your numerator is decreasing in the first quadrant and your denominator is increasing in the first quadrant. That means in both cases your cotangent is decreasing like crazy. Okay? Then at the half pi's, pi halves, cosine goes to 0, sine is 1, but you're at 0. So you're starting high, coming down to 0, then you go negative and go to negative infinity. Well, that's the opposite direction from tangent. Tangent started here and went up, cotangent starts positive and comes down. So cotangent is always a decreasing function, tangent is always an increasing function. So that's the big difference to me. They're going opposite directions, okay? Now, certainly the asymptotes are different. The cotangent are the whole pi's, because sine is 0 at the whole pi. Your tangents, the asymptotes, are at the half pi's, because that's where cosine is 0, okay? Now, here is your most generic, pretty much, expression of a cotangent function. y is equal to a cotangent bx minus c. Again, I like to break the b out and do that other stuff with it. What does the a represent? Okay, for sines and cosines, it represents amplitude, or is related to amplitude. But remember, these don't have amplitudes. But what does that relate to? At the quarter pies, at the quarter periods, that's exactly it. This is going to be a +1 here, a -1 there. +1 here, -1 there. You know, at your quarter pies, or your quarter periods, that's going to be where the A comes into play. Okay? The B is related to the period, and how is it related? Pi over b, exactly. For sine and cosine, it's 2 pi over b. For tangent and cotangent, it's pi over b. You're absolutely right. And C then is related to the phase shift, horizontal shift, okay? And that's why I like to factor out the b. What they use is C over b, and that's the phase shift. If you factor out the b, then what you're left with, that constant, which I call C, that is your phase shift. So either way you want to do it. So what we see is what you've already mentioned. The period is pi, like tangent, unlike sine and cosine, and later we'll see unlike secant and cosecant. Those are all periods of 2 pi. Domain, everywhere the sign is 0, which is that you're in pi. Those are excluded from the domain. All other values are there. Range, just like tangent, all real numbers. Negative infinity to positive infinity. The difference is cotangents start positive and go negative, tangents start negative and go positive, okay? Left to right. Your vertical asymptotes are where your domain is not defined, that is that you're in pies. I like to put the dotted line there at the origin, at the y-axis too, but they don't. How is it symmetric? Just like tangent, respect to the origin, which means it's what kind of function? Odd function, exactly. Okay, good deal. Okay. Whew, I'm so out of energy. All right, let's do example 3. Sketch the graph of 2 cotangent x over 3. And I like to begin by identifying my parameters. Okay? What parameter do you see here? A is equal to 2. Now that doesn't relate to amplitude anymore, but it relates to something sort of similar. And what else do you see? B is equal to 1/3. Perfect. Okay? Now the A, we don't worry with amplitude for cotangents and tangents, or secants or cosecants. Only sines and cosines we worry with amplitude. Well, take that back a little bit, but we'll talk about that later. But what the A does tell us is what you're going to be at your quarter periods. Okay, so we'll come back to that in a minute. So let's deal with the periods then. What is your period? I should have asked it another way. What is B related to? The period. And how is it related? The period is pi over B, and your B is 1/3, so that would be 3 pi. There's your period. Okay, now what do we do with that period? Usually once we've discovered it, divide by 4. So your interval then, that's what I like to call it, will be 3 pi over 4, which is a rather strange one, but that's where we'll begin. Okay? So let's start our graph here. All right. Now, the thing you don't see, because it's not there, there's no C. C is 0. And what does that mean for you? Say again? No phase shift, exactly. Okay? And since there's no phase shift, at least your initial vertical asymptote is not moved either. And what is your usual vertical asymptote? First one for the cotangent? The y-axis. Okay, so let me see if I can get this to go red here. So I'm going to dot that in, that is your first vertical asymptote. Okay, I'll come back and do the rest of them later. Okay? Okay. So we've got some unusual interval here, 3/4 pi. So I guess I'm stuck with it. I was trying to think of an easy way to do it. My first tendency was do 1/4 pies, but that's going to drag things out so big. So let's just do 3/4 pi. Let's tick them off here. 1, 2, 3, 4, 5, 6, and negative 1, 2, 3, 4, 5, 6. And while we're here, we'll go on and do our vertical scale. We'll do 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5. Okay, something like that. So we're going, let's go on and label our horizontal. This is 3 pi over 4. Twice that would be 6 pi over 4, which would be 3 pi over 2. 3 times that would be 9 pi over 4. Yeah, okay. 4 times that would be 3 pi. Okay? And I'm not going to write anymore. Okay? I don't like it. Okay. Coming back this way, it's minus 3 pi over 4. Minus 3 pi over 2. Minus 9 pi over 4. Minus 3 pi. And then you could write some more if you wanted to. Okay? Let's just label this as 1, 2, 3, 4, 5, and 6, and negative 1, negative 2, negative 3. You don't really need these in there, but I'm just going to write them there for completeness sake. All right. Now, you know, because there is no phase shift, cotangent has its first vertical asymptote at the y-axis. And then where would the next one be? 1 period later, because a full period goes between that, right? So that's the 3 pi. So there's going to be our next one. So let me go back to my red here. All right. So at 3 pi we'll have another one, and at minus 3 pi we'll have another one. Okay. Good. Okay. Now, here is the place that I ask myself this question. Self? No. What's in between your vertical asymptotes? Say again? Yeah, 3 pi over 2 is exactly halfway, and what's going to happen there? That's your intercept, the x-intercept. So we can plug those in. That's an intercept, that's an intercept, that's going to be an intercept, that's going to be an intercept. Okay, got that. Now what happens in between your vertical asymptotes and your intercept? That's what? That's where your A comes in, exactly. Your quarter periods, that's where the A. So that's going to be a 2 here and a minus 2 down here. A 2 here and a minus 2 down here. Okay? A 2 here and a minus 2 down here. Okay. So we know that this graph is going to look something like that, something like that, something like that, and something like that. Okay? There is your graph of 2 cotangent x over 3. See how your parameters guide you in the way here. Sure, you don't have an amplitude, but that A tells you where you are at your quarter periods, either plus A or minus A. Okay? And the A, if that was a negative number, that would flip it across the x-axis. Then it would really look more like a tangent function, wouldn't it? Okay? Your B tells you something about the period. And once you know the period, you know if there's no phase shift there, your first vertical asymptote is going to be the y-axis, and then go a period, every period, right or left from there is going to be another vertical asymptote. Okay? Then midway between your vertical asymptotes are your intercepts. Plot those in there. And then as long as that A is positive, you start at +2 in the first quarter interval, and you go to -2 at the 3/4 interval. Okay? And now if the A were negative, then you flip everything over to the other way. It's pretty simple to graph. Okay? Any questions on that? All right. There is a checkpoint here that would probably be a pretty good one to do. Now the book likes to do the table and do the set the thing in parentheses following the cotangent equal to 0 and pi and doing all its thing, doing undefined and stuff. We did the same thing, but we just did it right on the graph. Okay. Any questions? Well, since they're going to do it, let me clear this out of the way and see how they go about doing it. I was telling you what they did. I should have just shown you what they did. Okay. They don't mess around with the A's and the B's and the C's. They go to the solving the equations. Okay? Which is fine. I mean, there's nothing wrong with that. It's a perfectly good way to do it. Okay? What does that give you? At x equals 0, you have a vertical asymptote, and at x equals 3 pi, you have a vertical asymptote. And that's a good way to go. Halfway in between those, you have your intercepts, and a quarter way in there, you have your plus A's and minus A's. Okay, so that's a perfectly good way to do it. Okay, so x equals 0, x equals 3 pi, you have your vertical asymptotes. Okay, and then at -3 pi, positive 6 pi, -6 pi, you know, every 3 pi you have it one period away. Okay, and then they do their table thing, and that's where they let the 2 come into play, and that means that the quarter interval, you're going to be a +2, at the 3/4 interval to -2. That's as long as the A is positive. Okay. So yeah, you can do this if you prefer that over what we did. Fine, go for it. It does the same thing. It just, to me, is more work. Okay, and I'm lazy. Okay. And here's the graph of it. Not bad looking either. About like mine, I guess. Maybe a little neater, but not much. Okay. Now, they didn't label the points as well, and that's why I like to go on and do that. Go on and do them by the quarter intervals. Rather than your pi's there. But you see, this is between 1 pi and 2 pi. That was 3/2 pi. So that's exactly right. And this is at 3/4 pi, which is right. And this is the 9/4 pi, which is right there. To me, it's easier to plot when I have the actual quarter intervals in place. But if you prefer that way, it's fine. That maybe is better looking. I don't know. You decide. All right. That was example 3. Now we're moving right into graphs of reciprocal functions. Well, cotangent was a reciprocal function, but they mean the other two, the reciprocals of sine and cosine, which are, of course, secant and cosecant. Exactly. Okay. You can obtain the graphs, and this is what we do too, of the remaining 2 trigonometric functions by first graphing their reciprocal function. Graphing the sine and the cosine because we know what those are, right? And they're easy to graph, okay? So first graph the sine and the cosine corresponding to whatever your reciprocal function, cosecant or secant is. And everywhere that sine is a 0, that cosecant's got to be a vertical asymptote. Everywhere the cosine's a 0, your secant's going to be a vertical asymptote. So that's why we graph those first, okay? That's the first thing we get from them, your vertical asymptotes, okay? Now, Next thing you get from them is, when you do your sine and cosine, you go through the whole work. A, B, C, D, right? And you figure out what those are going to do. So all your work is done doing the sine or the cosine. Once you get them graphed, and everywhere that either sine or cosine is a 0, put your vertical asymptotes in. Okay? Now, where your sine is a max, the cosecant is going to kiss it right there. Where sine or cosine is a min, the cosecant or secant is going to kiss it right there. But then they go in the opposite direction. So from there on, you just graph it. It becomes really, really easy to do. You do all the work in setting up the sines and cosines, and then to do the secant and cosecant is just really easy to do. Of course, when cosine is 0, the reciprocal does not exist, so that value you're going to have vertical asymptote, which will be just like your vertical asymptotes for your tangent function. Where cosine is 0, because tangent is sine over cosine, and secant is 1 over cosine. So they're going to have the same vertical asymptote. Cotangent is cosine over sine, and secant is 1 over sine. Those will have the same vertical asymptote. So you'll set them up the same way. It's just where you go from there is a lot easier. In other words, the graphs of tangent x, which is sine over cosine, and secant, which is 1 over cosine, will have the vertical asymptotes at your half pi's. Okay? And whereas your cotangent, which is cosine over sine, and cosecant, which is 1 over sine, they'll have vertical asymptotes at your whole pi's. Okay. So to sketch the graph of the secant or cosecant function, first make the sketch of this reciprocal function, the sine or the cosine. Okay? And then everywhere sine or cosine is 0, it's going to be a vertical asymptote. And where you have max or mins, they're going to take off and go in the opposite directions. We'll see that. Okay? And here we'll see it right here. Here is your sine function. The gray function is your sine function. Here, the gray function is your cosine function. So everywhere the sine is 0, vertical asymptote, vertical asymptote, vertical asymptote, vertical asymptote. Right there. Okay? Now, where the sine is a minimum or a maximum, they're going to kiss there. Okay? But then they're going in opposite directions. So you don't have to worry about plotting anything else. Just have a touching here, and then going toward the vertical asymptotes. Touching here, going toward the vertical asymptote. Touching here, going toward the vertical asymptote. Away from the sine and cosine. If you think about it, all along we said sine and cosine are always between plus or minus 1. Secant and cosecant are always outside of plus or minus 1. Less than minus 1, less than or equal to, or greater than or equal to plus 1. They'll never have values in here. Ever. Okay? Same thing with secant then with cosine. At the zeros for the cosine, at the half pi's, put your vertical asymptotes in. And then at the max, they'll touch and go in the opposite direction. 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 Everywhere you have a max or a min. And that's all there is to graphing secants and cosecants. All the work is expended graphing the sine and cosine. Okay? So what does that mean about the secants and cosecant? Because you use the graphs of sine and cosine, they have the same period, 2 pi. Okay? Now, domains for cosecant function will be where your sines are 0, so that's your n pi's. All the x's except the n pi's. The ranges, now these are a little bizarre, they go from negative infinity up to -1, and positive 1 to positive infinity. They never are between -1 and 1. Okay? But they do include plus or minus 1. Vertical asymptotes are where your domain is not defined. That's your n pi here. And they're symmetric. This is the cosecant function. Is symmetric about the origin because it's reciprocal sine, which is symmetrical about the origin, which means it's what kind of function? Very good. Same thing's true, except that one last thing, well, a couple things. Your period's still 2 pi because the cosine period is 2 pi, so your secant period is 2 pi. Here your domain is all values of x except your half pi's, because that's where your cosine is 0. So just draw it. That's why you draw the cosine first. Everywhere it crosses the x-axis, go across and turn. Okay? Then the range is going to be just like it was for cosecant. Everything less than or equal to -1, greater than or equal to +1. So you write this as negative infinity to -1, parentheses by the negative infinity, bracket by the -1, because it can have that value. Okay? Bracket by +1 and positive infinity, parentheses. Vertical asymptotes are exactly where your zeros are, which is your half pi's. And it's this one's symmetric about the y-axis because of cosine y. So what does that mean? It's an even function. Okay. Good deal. Any questions on that? All right. In comparing the graphs of the cosecant and the secant functions with those of sine and cosine function, note that the hills and the valleys are interchanged. If you're at the top of the hill of a sine, you're at the bottom of the valley for the cosecant. If you're down at the bottom of the valley for the sine, you're at the top of the hill for the cosecant. Okay? They touch there and then take off in opposite directions, which is what we know anyway, because sine and cosine are always between plus or minus 1, and secants and cosecants are always greater than +1 and less than -1, or equal. Okay. For instance, a hill or maximum point on the sine curve corresponds to the valley or relative minimum on the cosecant curve. The valley on the minimum point on the sine curve is a hill on the cosecant curve. Same with cosines and secants. Additionally, the x-intercepts of the sine and cosine functions become the vertical asymptote. I already said that with the secant function perspective. Because you can't ever divide by 0, and that's where that would be in your denominator. The wind's picking up somehow. So let's do example 4. Yes? Sure. You say be excused? Is that what you said?
Yeah.
Yeah, sure.
I mean, I'm going to be like gone for a while.
Okay, that's fine.
Finish something, so I might not be back.
Okay, well, I mean, I'm recording, so you can pick it up later if you need to. And I'll be here till 10:45 if you can't get back. So, okay. All right, so here we have sketched the graph of y is equal to 2 cosecant of x plus pi fourths. So what would you do first? Second? Okay. Actually, second? A little louder. First, when you have secants or cosecants, do the reciprocal. What is the reciprocal of cosecant? Sine. Okay. So let's first graph the sine. Y is equal to, and do all your A, B's, and C's, and D's, or whatever you got, just like you would for a sine. 2 times the sine of x plus pi fourths. Okay? Now you do what you just said. You do your A, B's, and C's. What's your A? A is equal to 2. And since you're dealing with sines, that will correspond to an amplitude. We'll come to that. The amplitude is the absolute value of it, so the amplitude is also 2. Okay? Next. And what's your B? 1. Okay, and what does that relate to? Period. And what is your period then? 2 pi. Perfect. And then this one we do have a C, and that C is pi fourths. Actually, here's where you have to be a little careful. It's minus pi fourths. Remember, anything dealing with the x, you have to go in the opposite direction. Okay? So it's a minus pi fourths, and that has to do with what? That is your phase shift, or your horizontal shift. Okay? Let's go back to the period for a moment. What do we get from the period? The interval. And what's the interval? No, the period is 2 pi. What do we do with the period? Divide by 4. So that would give you the interval would then be pi halves. Except you got a phase shift of a pi fourth. So we're actually going to use pi fourths as the interval in this case, but not in one sense, okay? So let's set up my graph here, okay? Now, I'm going to tick off some points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we'll go up. 1, 2, 3. Ooh, really uneven here. And negative 1, 2, 3. Really uneven. Sorry about that. Okay? So let's put these as pi fourths. Pi halves, pi, 1, 2, 3, 4, 2 pi, okay, minus pi fourths, minus pi halves, minus pi, 1, 2, 3, 4, minus 2 pi, okay? We'll go up 1, 2, 3, 4. We don't need any more of those. Minus 1, minus 2, minus 3, minus 4. We don't need any of those. Just let those keep going. Okay. So we first are going to graph our sine function. Okay. Now there's a couple of ways you can interpret this question, and I want to hear them both. Where does sine begin? Okay. And most of the time, that's the answer to both questions. On the x-axis, it begins at 0. On the y-axis, it begins at 0. Okay? But because we have a phase shift here, where will this one start? Negative pi fourths, that phase shift. And that will be our 0 for our sine. Okay? And then we'll go our quarter interval, or our interval, which is pi halves, which is 2/4 pi. So the sine will go up to 2, or the maximum, at pi halves past that phase shift, past the minus 1/2, and then 2 more, we come down, 2 more, we go down to minus 2. 2 more, we go back to 0, and 2 more, we go to the max, and 2 more, we go back to 0, and so on. Coming this way, 2 quarter pi's, which makes one interval. This one goes down to minus 2. This 2 more, it goes to 0. 2 more, it goes to plus 2. 2 more, it goes to 0. Okay. That's your sine function, which we really will draw just because it's going to make our other easier. But that's not part of the problem. I mean, it's part of our solution, but not part of the problem, really. Right? But get it in place. Okay. Now, what's the first thing you probably ought to get out of that sine function? Vertical asymptotes, and where do those occur? Where the sine is 0. So there's a 0, 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 and there's a 0. Got it. Okay? Now, I want you to pick a different color for my cosecant function. Green, green, it's green, they say, on the far side of the hill. Okay. So, where are we going to do our cosecant function. That's what they're really asking for. The sine function did all the work you need to do. Now you just find those peaks and valleys and go in the opposite direction. So here's a max. So you just go toward your vertical asymptote there and toward your vertical asymptote there. Here's your min. Go toward the vertical asymptote, toward the vertical asymptote. There's a max. Toward the vertical asymptote, toward the vertical asymptote. There's a min, toward the vertical asymptote, toward. You see, all you're doing is going in the opposite direction. That's all it is. You don't have to worry about any other values. Just kiss at those peaks and valleys and go in the opposite direction. Got your vertical asymptotes in place, so head that way. All the work is spent doing the sine and cosine. Once you have those done, secant and cosecant, just head from there. Pretty easy, right? Okay. Any questions? All right. That was example 4. Okay. Let's just see how they did it. I'm sure they're going to have some changes. Let's see what they are. You began by sketching the graph of, just write it down exactly as it was there, only put a sine in rather than the cosecant. Okay? And then, what they're going to do, for this function, the amplitude is 2, so they did identify that, and the period is 2 pi because the b was 1. So they did do what we did, okay, in that sense. Then they go to these equations, which works fine. What we just did was, once you identified the c, which was minus pi-fourths, that's the only little trick here, that's where you begin at 0, and then you do your sine from there, okay? But they do it this way, which is fine, perfectly good. It starts at the same place, x equals minus pi-fourths, and then you're, one period later, you're at 7 pi-fourths. Which, if you go back and look at our graph, oh, I already erased it, you'll see that's where it reaches the next peak, okay? No, I'm sorry, the next 0 in the same direction. You can see that one cycle of the sine function corresponds to the interval from minus pi-fourths to 7/4 pi. And if you did yours, you'll see that too, okay? Now, once you have that graphed, and the amplitude being 2, so it went up there, your 0 at minus pi-fourths, your maximum then would be pi-halves later, which would be at positive pi-fourths, your 0 here, which will be your vertical asymptote, 3/4 pi, and your minimum down here at 5/4 pi, and your completed period is 7/4 pi. So 0 to 7/4 pi. Now that's one period for sine. You have 2 vertical asymptotes in there, but that's only one period for sine. And cosecant, because you have to have the down up part and the down part to make one period. So there it is. Basically the same thing we did, only my emphasis was, just like theirs, draw the sine function first, draw the vertical asymptotes through the zeros, and then peaks and valleys are your touching points and going in the opposite directions. Okay. Any questions? I'm losing it fast, folks. I'm so sorry. Because the sine function is 0 at the midpoint and endpoints of the interval corresponding cosecant function, that has vertical asymptotes at those zeros. I didn't identify them, that you could have, but everywhere across the x-axis, put a vertical asymptote. I mean, it's done for you. Okay? The graph of the cosecant function is represented by the black curve on that previous slide, which we saw. Now, they're skipping example 5. Okay. I hate to do this, but let me run to my office and get me another swig of something, because I am really losing steam fast here. So I'm going to pause this for just a moment, and I'll again. Okay, let's do example 5. Now, something I've noticed about this new edition, not always, but some of the times when they don't have the example on the slide set, they'll have, you'll see right under example 5, see larsonprecalculus.com for an interactive version of this type of example. Okay, so not only will you have larsonprecalculus.com for the checkpoint, you also have this very example or one like it. So this one is sketch the graph of y is equal to secant of 2x. Y is equal to secant of 2x. Where would you begin? Yes, do its reciprocal function, be y is equal to cosine of 2x. And then what do you do with that? Okay, and what's your a? 1. That means the amplitude's going to be 1. Okay, next. B is 2. That means the period is going to be pi. 2 pi over 2, which will be pi. Perfect. And your rest of them are 0. No phase shift, no C, no D, nothing. Okay? So, you got that. What do we do with the period? Divide it by 4, so your interval of interest is going to be pi fourths. Okay, so let's see if we can get our function in place here. Our intervals are going to be pi fourths, so let's do 1, 2, 3, 4, 5, 6, 7, negative 1, 2, 3, 4, 5, 6, 7. We'll just have going upward 1, 2, 3, 4, 5, 6, negative 1, 2, 3, 4. Okay? This is going to be pi fourths, pi halves, pi, and on, minus pi fourths, minus pi halves, minus pi, and on. This will be 1, 2, 3, and on, negative 1, negative 2, negative 3, and on. Okay. Okay. Now, let's go on and graph cosine of 2x. Where does cosine normally begin? At 1. Okay, so there we are, no phase shift, so we'll start there. And then one interval later, we'll go down to 0, and then down to minus 1, up to 0, up to plus 1, down to 0, down to minus 1, and up to 0. Going in the opposite direction, you go down to 0, down to minus 1, up to 0, up to plus 1, down to 0, down to minus 1, and back up to 0. Okay? So this is going to be your cosine function. Pretty simple, straightforward. I just don't draw very well. Okay? Now, once you have that in place, what do you do next? So I got vertical asymptote. Good idea. Where do those fall? Everywhere the cosine crosses the x-axis. Vertical asymptote there, and there, and there, and there, and over here, and here. What's that guy who teaches painting on some of those cable things? And then you do this. Oh, yeah, okay. I feel like that. Yeah, you do it here, and here, and here, and here. Yeah, I just don't draw as well as he does. Okay. So there are our vertical asymptotes in place. And now what do we do? Okay, so let's first pick a color for our secant function. Green again. I was thinking that might happen. And find your maxes and mins. That first max, go up from there. Your first min, go down from there. Your next max, go up from there. Don't cross those vertical asymptotes. I'm being a little sloppy here. And your next min, go down. Your next max, go up. And next min, go down. Yeah. Just make them nice, smooth curves. That's it. All the work is done in getting that cosine function in place. And once you have it done, found those zeros, going to be your vertical asymptotes. Then your maxes and mins, they're going to be your peaks and valleys of the others. So you got it. All right, make sense? Okay. Whew. All right. Any questions before I move on? Okay. Now we're going to do what y'all been thinking we've been doing all along, except you didn't put the P in there, okay? We're going to do damp with the P trigonometric graphs. Okay. Now, I don't know if you remember back in your Math 112 when you had combinations of functions. You added them together, you subtracted, and you multiplied and divided. You know. Well, we're going to sort of be doing a product function here. You can graph the product of two functions using the properties of the individual functions. Okay? Now, if one of these functions is a trig function, then the other function can be a damping function, and sometimes it doesn't damp, but it explodes or expands like crazy. But we'll start with this one, x times sine of x. So think of that as a product of the one function y is equal to x and the other function y is equal to sine x. Okay? Now, sorry. You know this function always stays between plus or minus 1, right? This function is the identity function. It goes up the vertical diagonal here, negative diagonal there, okay? However, since the sign can be plus or minus, you have to let the, this one, since you multiply them together, this one will always have a positive sign if it's positive, negative sign if it's negative, but this could be positive or negative, so you really have to graph the other function. Now, here's, the book doesn't approach it this way. This is how I think of it. And if you find this helpful, go for it. If you don't find it helpful, then go the book's way. I look at this, what would normally go here in front of sine? A, okay, good. Raising my finger, okay. And what do we call that? It relates to the amplitude. So what I think of this is a variable amplitude. When x is very small, your amplitude is very small. When x is very big, your amplitude gets very big. So therefore, this function here becomes an envelope in which your other function does. And you do the plus and the minus of it, and that gives you the dampening effect when you get close to zero, the expansion effect when you get far away. Okay? Now, since you know that, and this is how they approach it, and I'm okay with it, but it just seems a little awkward. Since the absolute value of sine is always between plus or minus 1, so in other words, absolute value of sine is less than or equal to 1. Okay. you have that 0 is less than or equal to the absolute value of x times the absolute value of sine, and this is also less than the absolute value of x. In other words, what they've done is multiplied this inequality, just put a 0 less than or equal to here, multiply this by absolute value of x. Absolute value of x times 0 is 0, absolute value of x times this is sine, absolute value of x is just that times 1 is that. So, to me, this is a little awkward, but it's true. Everything's true that they're saying here. And so we have, if you take off the absolute values in the middle there, then you have minus the absolute value of x on this end, x sine x there, and absolute value of x there. Okay. Rather awkward, but it's true. Okay. All they're trying to get to show you is, in my mind, is trying to justify why you have to do the minus x and plus x. And if you say, well, the amplitude is positive or negative, then draw them both in. Makes your envelope. Which means that the graph of alpha of x equals x sine x lies between the line y is equal to negative x and y is equal to positive x. That, to me, is what I call my envelope. Okay. Furthermore, okay, alpha of x is equal to x sine x is equal to plus or minus x wherever your sine is at your max or your min. And that's going to be at your half pies. Right? And that even though the envelope is taking off like this, when sine x is 0, that makes the your envelope, your whole function, equals 0. Even though you multiply it maybe by a huge number, times 0 is still 0, that's everywhere that you have your thing. So in other words, your key points for your sine, your intercepts are going to still be at n pi, and your max and mins are going to be at the half pies. That's what it's saying to you. Now, they don't mention it here. Okay. Yeah, what they talk about here. So, and what's the max and min going to be? Your envelope. No longer plus or minus 1, but plus or minus x. That's why I call it your variable amplitude. Okay? Okay? So all this that they're saying is absolutely true. Only thing that you have to watch for is this. Think about this. Your sine function starts at 0 and goes positive. And your x function starts at 0 and goes positive. So the product of those is going to be positive. But sine function normally went negative here, but your x function would have gone negative too, so the product there is positive. So that's the only thing you have to watch for. Both of these are odd functions, and odd times odd becomes an even function. So that's the one place that they really don't, they show it, but they don't say anything about it. But the product of these two is when x is positive and y is positive, of course those are positive. So in the first quadrant that's true. When x is negative and y is negative, which is in the second quadrant, they're both positive. So you have to come up here rather than going down here. But then once those are done, at your half pies, you have your maxes or mins, and your whole, and at your whole pies, you have your zeros. So your intercepts are going to be exactly like they are for sine. It's just that you have to remember where to go at the half pies. That's going to be your max and mins, which is going to be on your variable amplitude on the line y is equal to x or y is equal to minus x. That's what you got to do there. Okay. We will start next time with example 6, which is a different kind of dampening function, okay? So we'll begin at example 6. Now, they didn't have there it is. The factor X is called the damping factor. I like to call it the variable amplitude. That's just my preference in talking about it. Okay? They call it the damping factor, which is and that's why they call it damped trigonometric functions. Okay, homework exercises. Let's get those in before you leave. We almost finished 4.6. I think you can do all of 9 through 14. Now, only the odd answers are going to be in the back, but those are pretty easy to pick out. So I would say do all of 9 through 14, but check your answers for the odds. And then you can do any of the odds 15 through 37. They're all at calcchat.com, only 19's at calcview.com. You can do any of the odds 39 to 47. They're all at CalcChat. None of them are CalcView. Do any of the odds 49 to 55. They're all at CalcChat. 51's at CalcView. Do all the odds, or any of the odds you want to, 57 to 63. They're all at CalcChat. Only 57's at CalcView. And then stop there. And we'll do the rest of those after we do the damping. Good deal. Any questions? Sorry I had to take a stop in the middle, but I do feel a lot better now than I think I would have had I